Hi everyone, my name is Jason Koo, and today I want to show you how to use LangChain with MCP servers, namely with Neo4j's MCP servers, and also use Ollama so you can run this all locally for next to nothing. As usual, I have sample code for you to download and run, so we're going to start off with this repo, and I'm just going to walk through how to pull this in and run it, and then go into the code afterwards. So the first thing is to copy the GitHub code here, and then go to your favorite command line tool, put in git clone, put in that address, and then move into that folder project, and then run uv sync if you have UV installed. After all the dependencies are loaded, go ahead and copy over the env.sample file to a .env file. Then using your favorite IDE of choice, go ahead and open this up. Then in the env file, go ahead and update any of the Neo4j credentials that you have. You can optionally add in the Aura client ID and secret if you want to make use of the Aura Manager MCP server, but that requires a paid account, so I'm not going to demo that today. So actually, you can update the env file with any text editor. That would work just as well. Once this is updated, go ahead and run uv run main_fastapi.py. This is the file for running a FastAPI server. That we'll demonstrate later. Then in another terminal window, go ahead and spin up the Streamlit app, uv run streamlit run main_streamlit.py. Try to squeeze in Streamlit as much as possible here, and go ahead and run this. Now here is the final demo app that we're going to be walking through later. Here we've got a drop-down for selecting different LLM models, a chat interface, and then a simple graph viewer. So in this PyViz plugin, you can see here that we've got a small data set displayed here. So when you click on different nodes, it'll display the label at the top and then any properties on the bottom. Here I'm selecting Qwen3 just because in my testing, I've had the best response from Qwen3, but Qwen is definitely the slowest of the models that I've got available on my system. Okay, just asking a simple question. How many products are there? And you can see because I've got the Neo4j MCP Server server hooked up with the read Neo4j Cipher tool available, Qwen3 made use of that, called it, and got an answer of 7 products in the database, which is correct. Okay, and again, this is a drop-down for choosing various models where I could ask different questions or the same question again. But I will come back to this. So going to code, we've got kind of 2 options for adding MCP servers to a LangChain setup. And this first one I'm going to demonstrate is the simplest option that I've kind of found. And I just called this file main_simple. So here we've got a main block just so I can run this as a script to test. So here I'm just defining which model I want to use and then passing in a string request, then passing that to the agent with the model preferred. The run agent function is the meat and potatoes. Here we're using a context manager to run the studio client. This is for a standard in-out MCP server. And we're passing in a server params function, which defines the MCP server to use. I'll show that in a moment. Once this connection is made, then we're using another context manager, client session, to create the actual agent session. So we have to initialize that first. Then we're going to load up the MCP tools that were defined in the server params. And we're going to take those tools and we're going to pass it to a create React agent, which is actually a LangGraph component. And then we're going to invoke it by passing the original request into that agent. And just because when I'm switching different models, I noticed that the responses can be quite different. So I have a interpreting agent, which will then take that answer and kind of turn it into kind of a simpler answer. And then I'm just going to return a dictionary with the original response and then the interpreted answer. Okay, and this is the code for the interpreting agent, which is actually using the same model as the one that was using the tool call. But here it's given explicit prompt instructions to take the original request, that tool response, or that original agent response, and provide a kind of more comprehensive or a simpler answer. And then here at the bottom, depending on the LLM, it sometimes I had encountered where either it didn't run the invoke command or it preferred the A invoke command. So just put this here so it'll handle both options. And I have a helper function, extract content. So if the return object happened to be a dictionary, to pull out the content dictionary, this is actually really not necessary. You could just stringify the whole thing and just pass that back, would have been fine. And then I have a simple function for returning instances of the chat Ollama object, depending on the model name, just because of switching models so often. This becomes very convenient later on. And here, this is where the actual MCP configuration is set up. So we're creating a standard in-out server param object, and we're passing it in the MCP configuration. You will notice this is very similar to like a typical dictionary MCP configurations that you would use in other tools, except transport is explicitly defined, right? Transport standard in-out. So streaming HTTP and SSE setups would be different. And then the last argument, we have the environment arguments. Rather than explicitly passing the target keys and values in, I'm kind of cheating here by just passing it in all the environment variables. And the MCP server will, this one in particular, will just make use of the ones it was keyed to use and ignore the rest. Here, I'm just going to run this as a script just to make sure that it works. And it does, great. You can see here in the raw response, we have the agent, the original agent response. And in it, we can see that it made the tool call to the read Neo4j cipher tool. And I can even see the cipher query that it used to run. And then here, partially cut off is the answer. So this is the interpreted answer. So the rest of it here, there are 28 nodes in the graph. Okay, so this is great for a single MCP server use and will get you started. Very likely, very quickly, you will want to add in more than one MCP server to an agent. So here I created another file called main_multi, and this demonstrates how to set that up. So first thing I'm doing is I'm importing kind of some of the convenience functions I had from that simpler setup. Now here in the MCP server configs, this is a dictionary for defining all the MCP servers I want to pass into an agent. One option for adding in all these tools for an agent is you could actually run that similar pattern before of the nested context managers, start the initialization, and then load the MCP tools, take those tools, kind of run this through a cycle, and compile this all into a list, and then pass that list to the agent. This actually works, but as you can see, it's not very elegant. What would be better is to actually just make use of LangChain's multi-server MCP client, in which case you can just pass that configuration I showed earlier, and then you can do run client get tools, and it will load up those tools. Next, I created a multi-tool agent class just to simplify reusing some of this code. So this will store the model that was selected, the config options, the React agent, and then any of the tools that were created from that config process. Not sure I needed to go that far. Probably could have been just fine with just the model and the tools in the agent. Anyways. Okay. So in the initialize function, you can see here we are getting all the tools and then creating the React agent and then just initializing it with those tools. Again, we have this wonderful run request function. Here it's just making sure itself that the agent is available and initialized. And here I wanted to track how much time it was taking to process these requests. And then optionally, I wanted to see if I could get more logging information from LangChain as it was running. So that's what this if with logging is enabled. In the end, I didn't find the information that it provided was all that useful. Really, these are the two main functions for this to run, which is to invoke that message to the underlying React agent, and then taking that response and again passing it through the interpret agent response, and then returning all that as a simple dictionary payload. And then a main function block just to allow me to run this as a script again. Obviously, after a while of running this and trying out different questions, got tired of constantly just changing the text there, so created a interactive version which just loops the multi-tool version and so that in a CLI, I could just ask it continuous questions. Now, this one, I did not add memory, so every question is basically going to be new to the LLM. It won't be able to make use of, say, error handling. Okay, so here we're just initializing that multi-tool class that we created, and then passing it to this function that kind of runs this in a while loop. So here, while the user input isn't exit, it will keep taking that user input from the CLI and just run it into that agent to process questions, statements, etc. So here I was using Ollama for testing, and as you can see here, it was able to answer the first question fine, and the second question, it wasn't quite sure what to do. And I found that if I made the statement more explicit, it will know to use the right tool and make the right call. And sometimes I have to be even more explicit, right? Like use this tool from this server to do this thing, and then got the result I wanted. Now I can take all this and move it into a FastAPI server. And here, just creating kind of a cache for the agents. Because I'm going to be switching models so much, instead of reinitializing basically the same agent over and over, just going to hold on to the agents by the model name. And then the single API endpoint, which is just query. Here, this is all just niceties for presenting information and examples to the FastAPI interactive docs. In the function itself, just making sure we actually have a command that was passed in, and then getting the appropriate agent for the model that was selected, and then passing that command right into that agent. And then just formatting the response and passing that back, and also catching or returning errors as encountered. And here we've got just another way of spinning up a FastAPI server through a simple Python call. Here we have the server running and the interactive docs available. Again, you can see we got a single query. And if you want to try it out, we've got already a command that you can run right out the gate. But I don't want to write anything, so I'm just going to change it back to our how many nodes are there. And this is what the response looks like. And now the Streamlit code, again, we're using PyViz for the graph visualizer. It's loading up the env variables. And you can see here in the model options, here, just manually put in the names of the Ollama models that you have available. It didn't go through the process of creating a script to auto pull these. Just fine, just run Ollama list, you'll see the name, and then you can just add that to here. To provide the information for that PyViz network chart, we're just using the Neo4j driver directly and just going to call it here in the driver session. Just going to do a simple cipher call, grab all the nodes up to the first 100, and then parse through this for use by PyViz. All right, and I wanted all the different node labels to have a different color just so that they're more easily distinguishable. So this simple function just takes all the available node labels from the database, and it will assign each label a different color, trying to space it out as evenly as possible so that there's a good contrast. And then this update graph call is actually for updating the data for PyViz. So here it's just making that call to Neo4j, and then just assigning all the different colors, and then creating all the PyViz nodes and edges. And then here, get API URL. So this is for communicating with that FastAPI server that we spun up earlier. Now, this could be replaced with just a direct call to that multi-tool instance as well. And then in this main function block, this is just creating all the interface for Streamlit. So title, creating a chat history session, which model was used last, and then doing just a 2-column layout. And then we're using the Streamlit chat input plugin. And so every time a user provides an input, hits return, it will populate that user input variable. It will add that to the session state history. It will pass that request to the FastAPI endpoint, get an answer, and then post that answer also to the history. So every time Streamlit reruns, it will update and that chat history will populate. And in the second column, that's where we have the PyViz graph viewer. Here, it's just displaying that network graph with the Neo4j data. So here I'm just showing again the Streamlit app, and this time showing that same question going to Llama 3.2. In this particular run, I discovered that I just couldn't get Llama to answer that question that it had done previously. So then, of course, it got me thinking, like, goodness, how am I going to figure out which of these models is best to use with this particular setup? So I created a very simple test evaluation, which is located in the test_multi.py file. So here you can see I've got just a simple set of questions and expected answers in a list. And I'm just going to take this list and I'm going to run it against the various models that I have available and test it multiple times so I can get kind of an average. Now, this is a very simple test. Probably should have used a testing framework, but I didn't want to add any additional dependencies for this particular demo. Here in the calculate averages, this is the function that kind of kicks off the testing. So it will go through each of the models I've defined. It will spin up a multi-tool agent for that model. So with each of those evaluation questions, it will pull it up. It will go, okay, this is the question and these are the answers I'm expecting. And then for the number of iterations, it will just run that request against that agent. All right, so as we're looping through, this is how this function is checking for the correct answer. So here it's just seeing if the expected answer is anywhere in the response from the agent. This is a very simple test. It works with numerical answers just fine, but this is not very good if you're expecting a string output. There are way more robust types of tests that you can be doing for this sort of thing, but for something quick and dirty, this worked for me. And here we're just compiling all that data and then displaying it. Okay, so here's from previous run. Those are all the log outputs that I had set up. And here we can see the final results from testing Llama 3.2, Mistral, and Qwen 3. You can see that Llama 3.2 actually ran, I thought, pretty fast, right? It was always about between 6 and 7 seconds. And in this particular case, it did okay, 33%. Unfortunately for Mistral, this particular test run, it didn't do well at all. And you can see it takes about twice as long as Llama 3.2 to come up with answers. And then finally, Qwen 3, this one, not only the test results were good, but in my own anecdotal usage of it, it was quite good. The only downside of using Qwen 3 was that it is between 4 and 5 times slower than Llama 3.2, so you have to do quite a bit of waiting. So what I'd probably do is I'd probably do simpler read queries using Llama 3.2, and then any sort of writes or very complex queries, I would switch over to Qwen 3. All right, so that was basically 2 different ways of showing how you can use MCP servers with a LangChain setup. Again, this was using Ollama, so you can make these calls or experiment all you want, and it will cost you basically next to nothing. Okay, I hope that was useful for you. Thank you very much for watching, and I look forward to seeing you in the next one.